parameters measured by the computer and the parameters controlled. We measure the voltages at the calorimeter boundary. The way we run our experiments is to run an isothermal condition. That is, a heater wound symmetrically with the electrochemical cell applies power so that the complementary power, you can just see the space for the helical grooves of a heater which is wound in this direction. The computer supplies power to the heater and to the electrochemical system, such that the sum of the two of them is held to be constant. In this way, we maintain constant power to the contents of the calorimeter, and the system will be isothermal, provided that there is no excess power source. The important thing here only is to measure your powers accurately. So we measure the voltages at the calorimeter boundary, the voltages for the heater at the calorimeter boundary, and also measure a reference electrode. We measure the two currents to give us the input powers, the power being the product of the current and the voltage to the cell and the heater. The temperatures, the bath and RTD, the inlet temperature 2 RTDs, the outlet temperature 2 RTDs and 2 thermistors. We also measure the room temperature. We measure the cell pressure, the volumetric flow, the gravimetric flow, and a multiplexed measurement between two electrochemical cells run in parallel. We also measure the palladium resistance, which is multiplexed to the resistance measuring device to give us the deuterium to palladium ratio. We control the cell current and the heater current in such a way that the sum of the two input powers is held to be constant, and we, under some circumstances, control also the bath temperature. I don't want to overburden you with this issue of sources of error, but it's important to consider what potential sources exist in such an experiment and look at the means by which you can come to believe that they're not important. The output power, as I said before, is described by this equation in terms of the heat capacity of the flowing fluid, the inlet and outlet temperatures, and the conductive loss term. The input power is the sum of the power applied to the heater, the power applied to the electrochemical cell, which is simply the current, the product of the current and the voltage. All of our electrochemical cells are closed, and any excess power source that you may have in the system. As it happens, these powers are measured as the the product of two voltages divided by the resistance, which is used to measure the current flowing to that element. Same here. For the electrochemical power, the product of the voltage at the calorimeter boundary, the voltage across the resistance measured, used to measure the current flowing to that element. Temperatures are measured with platinum resistance temperature devices, so they are measured in terms of the resistance of the RTD element, normally something like 100 ohms, where the coefficient alpha is the known slope of the temperature resistance coefficient of platinum. So that in terms of the raw measured data, the excess power is expressed this term due to the conductive transfer of heat out of the electrochemical environment. The resistance ratio of the inlet and outlet temperature sensors minus the known sources of input power. This particular term in square brackets has useful properties. This resistance ratio difference has a wonderful effect in reducing susceptibility to systematic errors. We have, therefore, three types of terms in this expression. The constants, which are predetermined, the heat capacity, temperature coefficient of resistance of platinum, the initial resistances of the temperature measuring devices, and the resistances used to determine the currents flowing in the electrochemical and heater power circuit. The calibration constant, the conductive loss term from the calorimeter, which is a small term, but one which is calibrated at the beginning of the experiment and repeatedly calibrated throughout an experiment. And the variables that are measured, the mass flow rate, the resistance of the inlet and outlet temperature sensors, and the 4 voltages. We're looking for potential sources of systematic error in these terms. Temperature coefficient of platinum, we expect no source of error and do nothing about it. Heat capacity, in our more recent experiments, in fact, all but one of the experiments that I will describe the results of, water was the heat transfer fluid. Its heat capacity is well known, and the temperature coefficient of that heat capacity is well described. In days when we were using silicone oil as a heat transfer fluid, and only one experiment will be described of this type, it did have the tendency to pick up moisture from the air, changing its viscosity and its heat capacity, and efforts had to be made to keep the water content of the silicone oil down. Temperatures measured through these resistance ratios, well, it's based upon a platinum element. To the extent that these elements are attacked by corrosion, then there might be some source of systematic error. Again, the currents determined via the standard resistances, the temperature coefficient of these resistances might lead to systematic errors, and attention must be paid to them. The conductive loss term can be affected by poor mixing. It's important to ensure that that there is some form of turbulence remover before the temperature measurement, particularly at the outlet. There might be some absolute error in the multimeter calibration. The way we perform our experiments, we use a single calibrated multimeter, and all measurements are multiplexed to that meter. We periodically interchange that meter with another calibrated multimeter, and we in general run 2 electrochemical cells, 2 calorimetric experiments in series. So one, in fact, acts as a blank with which we can refer the other. If we observe excess power in one, while we're not observing excess power in the other, then it's unlikely to be a source of poor calibration of the multimeter, and we must look to other sources of potential systematic error. The 4 voltage terms, well, we know how to measure voltages reasonably accurately, and we can periodically interchange the multimeter, the digital voltmeter, in order to ensure that this is not a source of systematic error. The mass flow rate, as I described to you, is measured by simply pouring the fluid into a volume on a digital balance and periodically pulling the variant. Having described to you some of the sources of error and the means by which we have attempted to remedy them, I will now describe to you our results. The results here are shown as just a limited range of experiments. We started in April of 1989 with 2 experiments operated at 1,000 psi deuterium. We observed apparently excess power in both of these experiments. We then attempted a series of high-pressure experiments which, for technical reasons, never attained the durations that we had hoped. And we observed no excess power in these high-pressure experiments. We then went for a rather unfortunate period of something like 7 months here in 1990, where we observed no excess power. We then began a series of experiments which I'm going to describe, beginning with P12, in which all during this time we've been doing our degree of loading experiments, trying to understand the parameters by which you can come to load deuterium into the